Hello everyone, I'm J Wildberger, and today we're talking more about sociology and pure mathematics. And I want to look at equality in mathematics. The reason I want to do that is because last time I pointed out the important distinction between a description of a set and an actual specification of a set. And there's obviously some possibility for confusion here, which I think lends itself to consequent insecurity in the foundations of mathematics. So to understand this a little bit more deeply, let's have a look at an essential notational aspect of the story, which has to do with equality, the equal sign in mathematics, and the various ways in which it appears. So it turns out that there's quite a variety of different interpretations of this equal sign, and so it's easy to sort of morph from one to another without being explicit about it, and that can result in confusion and misunderstanding. Okay, so the actual notational thing, the two bars for equality, goes back to a Welsh mathematician, Robert Ricordi, in around 1557. And it means is equal to. But what exactly that means, well, we'll see, has lots of interpretations. And so we should think about this kind of thing as part of an evolutionary development of mathematics, as notational devices and conventions morph through time. So in this video, we are going to talk about different usages of this equal sign. We'll also look at some variants, and we'll discuss briefly some logical confusions that may naturally arise because we have this multiplicity of meanings or associations for this sign. The first usage is a very strict equality. We could call it identical equality, where we say that two things are equal precisely when they really are the same thing. Okay, so that this symbol equals that symbol. They're the same, while this symbol and this symbol are different, so they're not equal. Actually, in mathematics, it's rare that we're that strict about equality. Usually we kind of agree that things are equal. They don't actually have to coincide, but they can be distinct, but they can share characteristics that we're interested in. So for example, these two markers here, okay, both blue markers, now actually they're distinct objects. They're not really equal as objects, but from many points of view, they are really to be thought of as identical. They're just copies of each other. Even though actually, if we looked at the physics of it, the weights would be somewhat different. The liquid content would be somewhat different, etc. Okay, a second usage of equality is, look at a statement like this. So if x equals 2, then x squared equals 4. That's a very familiar statement. So we've got equality being used here two different ways. So if x equals 2, so this is sort of an association of this variable or unknown quantity x, not entirely clear what that means, but we're sort of associating x to 2. And then we're making a statement that x squared equals 4. Okay, so we're using here the equal sign to be able to describe this statement of fact given by this statement. Here's another usage, evaluation. 5 plus 4 equals 9. On the left-hand side, we have an arithmetical expression, which is strictly speaking not a natural number yet, although it evaluates to a natural number, and the evaluation is to 9. So we say 5 plus 4 equals 9, but strictly speaking, the left and the right-hand sides have somewhat different aspects. Okay? This is an arithmetical expression that still has to be evaluated, and this is the result of that evaluation. Another important usage of the equal sign is in assignment. Assignment of a value to a variable. For example, let w equals 3. Here w is a variable, and we are assigning it the value 3. Computer science terms, we might think of w as a position in some memory location, and we're sticking 3 into that position. Sometimes we use some other notation, perhaps sometimes like the colon equals is used for assignment. I like to use a variant of the equal sign with 3 bars to denote assignment when I'm writing papers sometimes. Now there's some question about this. I mean, what's the actual nature of a variable in mathematics? And does it make sense? Or what is actually the meaning when we say let this variable equal 3, etc.? But anyway, this is a very important usage of equal signs. Another usage is in establishing equivalence between things. We have two things which are not equal on the face of it, but we want to regard them as equal in a particular context. So we have some rule that we assign that says, we'll say that this thing is equal to this thing if a certain condition is met. And the best example, perhaps the simplest example of that, is the equivalence of fractions or rational numbers. So 2 over 3 equals 4 over 6. We see that these are the same as rational numbers, even though visibly they're different expressions. And the rule that says that they're the same is, well, that 2 times 6 equals 3 times 4. Okay, that's the way we establish equivalence of rational numbers. Equality of evaluation. It's a little bit of a twist on this just evaluation that I've discussed in the previous slide. Here we have 5 plus 4 equals 3 times 3. Strictly speaking, neither of these is an actual natural number. They are both arithmetical expressions which evaluate to the natural number 9. And the statement here is that these two expressions evaluate to the same natural number, even though the actual natural number is not appearing here. Another usage as a definition, in this case of a quantity. So here's a segment from point A to a point B, and we could define L to be the length of this segment AB. So in this case, this equal sign is saying it's an assignment again, but it's assigning this quantity to the letter L. Closely related to that is this the idea of measurement and expressing a measurement. So the statement L equals 11 centimeters, which could apply to this thing here. If we get a ruler, we take this segment, and then we measure it, okay, we see 11 centimeters. Okay, so here is the definition of L given by an equal sign. Here's another equation involving L, which is telling us what L actually evaluates to, or what the measurement of L is. Here's another equal sign usage where we're talking about a universal identity, that the left-hand side equals the right-hand side. These are now general algebraic expressions. And we can think of A and B perhaps as variables, or perhaps as numbers that are just not specified. It's not entirely clear what we're talking about here. There's various possibilities of meaning or interpretation here. A plus B squared equals A squared plus 2AB plus B squared. So you can think about starting with the left-hand side and expanding it to get the right-hand side, or you could think about starting with the right-hand side and sort of factoring it to get the left-hand side. So in this case, the equal sign is expressing an identity of an algebraic kind. Okay, so now we want to get to the sort of knotty issue that I was talking about in my last video, this distinction between descriptions of mathematical objects and specifications of those mathematical objects. Okay, it's a very subtle issue here, and it's not entirely easy to get your finger on it. Okay, consider this set S. Here's S equals the set of primes P such that P is between 1 and 10. So I would say that's a definition, which is really a description. Okay, so it's a descriptional definition. Here's another set, T. It's given by the set 2, 3, 5, 7. Now these are all also primes, and in fact these are the primes between 1 and 10. So these sets are in some sense the same, but only in one sense. In another sense, this is a different kind of object because this is the definition of a set via a specification rather than as a description. So maybe like from a computer scientist point of view, this accords more with what actually would be in memory. Okay? While this thing here would be harder to parse unless you have some more sophisticated language capability to be able to interpret what these words mean, etc. Okay? This is a somehow more primitive, more fundamental object, and this is a sort of an English description of this thing. But here we come to this sort of interesting aspect of the equal sign that we generally associated with a transitivity. So we generally think that when we're talking about equal signs, that if we have A, B, and C, say three things, and if A equals B, and if B equals C, then necessarily A equals C. But that's not necessarily always so evident if we're talking about these sort of alternate or altered forms or interpretations of equality. So for example, these two sets, at some level they're the same. I mean, nobody would disapprove of the statement that this set equals this set, that S equals T. Okay? But that sort of obscures the fact that we really have two different kinds of definitions floating around here. Okay, maybe it's a little bit clearer if we up the ante. Here's set U, primes between 1 and 100, and here's V, which is my list of primes between 1 and 100. Okay? Now, it's more work generating this set. So one feels one has accomplished more than just by writing this thing out rather glibly. Okay? So maybe if you've just gone through the trouble of writing this down and someone comes along and says, oh, I've done exactly the same work just by writing this thing down, you might say, well, no, you haven't actually done the same amount of work. I've done more work. I've done the honest work. This is just at the level of talking. And there's probably some sense in which that's reasonably valid. So in the previous slide, we were able to obtain these explicit sets T and V. They were the actual lists of primes, without too much work from the descriptions. And so it appears to us that there's not such a big difference between the description and the actual specification. But if we look at something like this, where we up the ante very considerably, considering primes now between 1 and 10 to the 10 to the 10. So we can just as easily, state W equals this set. But now finding a corresponding specific set actually exhibiting this set is in this case, an impossible proposition. Right? This is far bigger than we're able to go in terms of finding primes uniformly. Maybe we might be able to find, an occasional prime close to this range, but in terms of finding all of them, okay, there's no way we can do that. And very likely, this kind of question is even impossible, in terms of the entire universe. Maybe the universe is just too small, doesn't have enough informational content to be able to actually specifically write out this set. So now the gap between the description and the specification becomes much more obvious. So syntactically, this looks just like the previous versions with the smaller numbers here. But in terms of the meaning, it's not at all really clear what this thing even means. And so the role of this equality sign here is now causing us to scratch our heads. What does it mean to say that W equals this? Okay, so I've raised some questions here. I don't necessarily have good answers for them, okay? I'm not sure how to best proceed in terms of removing this ambiguity, but I think we need to acknowledge that there is some ambiguity having to do with the multiple usages of this single notation, this very crucial notational symbol. And probably it would be more clear if we had a wider variety of symbols that were covering the similar territory so that we could more clearly distinguish between these different usages. Now, to a certain extent, we already do this. So let me just briefly mention some variants of the equal sign. We've already talked about this equal sign or this equal sign for assignments. Those are sometimes variants. Here's another one that's pretty close to an equal sign. It's sometimes an isomorphism sign, so it's used in mathematical theories when you want to say these two objects, they're maybe not exactly the same, but in the purposes or in the context of this particular theory, we're going to regard them as equal. Okay, and sometimes this is also used, of course, in geometry to refer to congruent figures. A related, somewhat weaker symbol is this double squiggle. Sometimes it's used to denote approximately equal. So this thing is approximately equal to that. Okay, not exactly equal, but approximately. And also in geometry, sometimes this is used for similarity. So we do have some variants of our equal sign, but I think still the entire discussion probably needs to be thought about more clearly. and carefully. And I think here is a good place where we can get our computer science and programming friends to help. And in fact, I hope to have a discussion with my friend Michael Reynolds about these kinds of issues where we can sort of see how the mathematics and the computer science points of view interact. I'm Norman Wildberger. Thanks for listening.